So, same chapter, electronics. And today we have to study about the types of negative feedback operational amplifier. There are two types of the negative feedback operational amplifier. Number one is called inverting negative feedback operational amplifier. Inverting negative feedback operational amplifier. Suppose this is operational amplifier. One of input is connected with the earth. So zero potential here. So this is non-inverted input. So it is zero. And then here is inverting input terminal. Voltage input is given through this resistor, and this resistor is called input resistor. So this is input. This is the input, and it is given to the operational amplifier by the input resistor. This is output voltage terminal. Now the fraction of the output is added inside the input to make the fraction of the output voltage. This resistor is connected for the feedback. So this is called feedback resistor, mean RF. So two resistor, one is input RI and other is RF. Now this terminal is P. Okay, so first of all, before switching on the circuit, look, output directly proportional to difference of the two input, but maximum output is plus minus supply. If output becomes greater than supply, then operational amplifier is called saturated. So before switching on the this circuit, we have to make some settings to avoid the saturation. So to avoid the saturation of op-amp, we will keep this output low. Output voltage directly proportional to input. When output voltage is less, then definitely the difference between two inputs must be less. It means if we keep the difference between two inputs voltage minimum, output voltage from the op-amp will be minimum. It will remain smaller than the supply, not the greater than. When output remains smaller than the supply, so this operational amplifier is not saturated. So I repeat, to avoid saturation, we have to keep this output voltage low, mean lower than supply voltage, but output directly proportional to difference of the inputs. For small value of the output, we have to keep this difference of the input minimum. So it's very important. keep the input difference of the two terminals, input voltage difference to terminal must be small to avoid the saturation. Then one of the input voltage is 0, so keep the distance low. This P must be at virtual earth potential, because this is 100% at the earth potential. We will keep this P close to 0, and close to 0 mean virtually earth potential. So when P is kept very close to 0 volt, mean at virtual earth potential, the difference of these two inputs will be less, output will be small. When output is smaller than supply, so this operational amplifier is not saturated. So for saturation, this is very important. Now suppose this input voltage is positive in polarity and the voltage at P is close to 0, approximately 0. Then look at this resistor, one side high potential and the other side low potential. So due to potential difference, current will flow from high potential to low potential, from left to right in the RE resistor, and according to Ohm's law, V is equal to IR. So this I current will be the difference of the two potentials. One is positive input, other side is approximately 0, and in between the resistance is Ri. So this current is V input divided by Ri. When this current I reaches at this junction P, according to Kirchhoff's first law, it is divided into two parts. Suppose part 1 is going here and the part 2 going in this. So according to the Kirchhoff's first law, at the junction P, we can write I divided into two currents, I1 plus I2. But remember, this I2 current is going to op-amp. And we have done that the input terminal impedance of the op-amp is infinity, or practically 10 power 6 to 10 power 12 ohm. So due to this very large impedance, large resistance, I2 current is negligible. So this I2 current becomes negligible, mean it becomes 0. So we can write I is approximately equal to I1, because I2 current is not possible due to very high impedance, very high resistance of the input terminal of the op-amp. Okay, now look at this I1 current. It is going towards feedback resistor, and then it is leaving from this. Now the current is flowing to the resistor from left to right. So definitely here at the left, there must be high potential, and at the right, there must be low potential. But look at the value of the high potential. It is virtually earth, 0. This is 0. So if high potential has the value 0, then what will be the value for the low potential? So definitely smaller than 0. So here the voltage will be minus negative. So the output will be the negative. So look, input is positive and the output is negative. That's why this is called inverting negative feedback op-amp. we are giving positive input and we are getting here negative output. That's why it is called inverting. Okay. Now this I1 current, which is flowing through the RF resistor according to Ohm's law, V is equal to IR, then I1 current will be the potential difference of the feedback resistor, one side negative and other side 0. So we can write minus V naught minus 0 divided by resistance RF. So this I1 is equal to minus V naught over RF. So look at I, it is input voltage over Ri, and and this I1 is minus V naught, mean output voltage over RF. Now come to this relation here. I is equal to I1. So if I is equal to I1, the expression for the I is input voltage divided by Ri. An expression for the I1 is minus V naught over RF. Now it can be written as V output voltage divided by V input voltage is equal to minus RF over RI. This output voltage over input voltage is the gain of any operational amplifier. So in this op-amp, gain is minus RF over RI. Mean the ratio between RF and RI is the gain, and this negative sign is indicating that this is inverting negative feedback operational amplifier. Okay, so this gain from the operational amplifier, which is V out over V in minus RF over RI, can be written as V out minus RF over Ri into input. Now suppose if the input is constant, this resistor is constant, and this RF, mean feedback resistor, is replaced with LDR, light dependent resistor. So in light dependent resistor, resistance decreases with light intensity. So if RF is replaced with the LDR, so when there is a bright light, when there is a brightness due to small resistance of the LDR, this output voltage decreases. Because when this constant, so V naught directly proportional to RF. So when RF is replaced with the LDR, in the bright light and the brightness, output decreases. But when the surrounding is dark, in the darkness, the resistance of the LDR increases. So the output from this operational amplifier will increase. And similarly, if this feedback resistor is replaced with thermistor, due to thermistor, when there's a high temperature, when there's a hotness, resistance of the thermistor is low, so the output from the operational amplifier decreases. But when there is a coldness in the surrounding, low temperature, resistance of the thermistor will be high. So voltage output from this operational amplifier will be large, will increase. Now, this operational amplifier, which is negative inverting operational amplifier, mean inverting negative feedback operational amplifier, One of the terminals suppose connected with the earth, and there are multiple inputs. This is suppose first resistor, this is suppose the second resistor, this is third resistor, and all resistors are joined, and the common voltage is given to the op-amp. This resistor input is R1, this is R2, this is R3, and this is V1 input, this is V2 input, this is V3 input, and here is the output, and there is a single feedback resistor connected with this input at P. This is RF. Now, this inverting negative feedback operational amplifier will multiple input is called multiplexer or mixer, mean it mixes many inputs for operational amplifier, and it is also used in analog to digital conversion. When analog signal is converted to digital, this type of the amplifier is used. Now, we have done that this is the output formula, output voltage formula. So here the output voltage formula will be minus common. So we will write step by step RF over R1 into V1 plus RF over R2 into V2, RF over R3 into V3, and so on. When number of the inputs are given to operational amplifier, then this will be the formula RF over R1 times V1, RF over R2 times V2, RF, and all these fractions, these values are added for the total output. So V out is equal to minus RF over R1 in V1, RF over R2 V2, and so on. And sometimes it is also written as minus RF common. We can write V1 over R1 plus V2 over R2 plus V3 over R3, and so on. And this is the formula when this operation amplifier is used as multiplexer. Now, the next one, the number 2 negative feedback operational amplifier is non-inverting. Negative feedback operational amplifier. So this is non-inverting. Positive input will give the positive output, and the negative input will give you the negative output. This is operational amplifier. This is its output terminal. So first of all, we will divide this output voltage into number of the parts, mean we will make the potential divider of the output. So 2 resistors for the potential divider at least. Suppose this is R1, this is R2. So here output voltage suppose is positive, and here 0 voltage. So this is high potential and this is the low potential. Due to potential difference, current will flow through this potential divider. And the expression for this current according to Ohm's law will be V is equal to IR. So I is equal to potential difference is V out minus 0 divided by total resistance R1 plus R2. So this current I is equal to V naught divided by R1 plus R2. This is the magnitude of the current. Now suppose from this point, a wire is connected with the input terminal of the op-amp. Suppose this is non-inverting, and this inverting is connected with the earth. So zero potential here, and potential value over this terminal will be exactly equal to any potential, any voltage across this, because resistor which is connected with the earth will deliver its voltage as an input. So the voltage across this resistor will be input for the op-amp. Now again, this terminal is P. Suppose when this current I is coming and it approaches P, it divides into two. Suppose I1 current is going here and I2 is passing through the second resistor R2. So according to the Kirchhoff law, we can write at the junction, sum of the currents entering is equal to sum of the currents leaving, which is also called the law of conservation of the charges. But look at the input terminal impedance. The input terminal impedance of op-amp is very high. Ideally infinity, practically 10 power 12 ohm. It's too large. So this I1 approaches to 0. So we will cancel this I1. So I is approximately equal to I2. So I current expression is already derived. Now we derive this I2. Look, according to Ohm's law again, I2 current is equal to potential difference. So the potential difference across this resistor is actually the input given to the op-amp divided by resistor R2. Now substitute these two values. I is V naught divided by R1 plus R2, and I2 is input voltage to op-amp divided by R2. Now it can be written as V out divided by V in is equal to R1 plus R2 over R2. Now this gain, which is output voltage over input voltage, can be written as R1 over R2 plus R2 over R2. This cancelled one left. So we can write V out over V in R1 over R2 plus 1. So this is the formula for the gain of operational amplifier, which is non-inverting negative feedback. So here, no negative sign. So if input is positive, so output will remain positive, and we can write this gain is equal to 1 plus R1 over R2. Now the next topic is use of any op-amp in a relay circuit. Use of the op-amp in relay circuit. Suppose this is operational amplifier and it is connected in any comparator circuit, either light intensity comparator or temperature comparator. We suppose it's connected with the light intensity comparator. We have done that. This is the output. And one diode is connected with this output terminal. It's not LED, it's a diode. And then diode is connected with a coil. This is the winding of the wire. And then this coil is connected with earth. Now here is a source of the electricity, alternating or direct anion. This is the copper wire. Then the next copper wire. And then source is connected, suppose, with a street light. Now this gap between the two copper wire has a strip of the iron. This is the iron leaf. And the circuit of this operational amplifier is designed as when there is a darkness in the surrounding, output polarity is positive. Meaning in the evening, this operational amplifier circuit gives output positive voltage. So this is 0. When the output is positive due to the darkness, this diode is forward biased because the positive connect with the positive. So it becomes conducting. Current flows through it. When current passes the coil, it becomes electromagnet, and then current passes through the coil to the earth. Mean when there is a darkness, output voltage is positive, diode becomes conductor. When current flows through it, it goes to the coil, so coil becomes electromagnet, and this electromagnet attracts the iron leaf in this direction. When this is attracted, it makes the contact with the other end of the copper wire. When this iron leaf touches the lower end of this copper wire, circuit is completed and street light goes on. Mean after the sunset, there will be darkness. Output will be positive. Diode is conductor. Electromagnet is there, which attracts the iron leaf. And due to attraction, contacts are made. Yeah, contact is made, and the street light goes on. For the whole night, there is a darkness, so there is a positive output, and the street light remains switched on. Now, this output is positive only when this non-inverted input is greater and this inverting input is smaller. Okay. In the morning, when the sun rises, there is a brightness. So due to the brightness, this output voltage becomes negative. So due to the negative, this becomes the non-conducting reverse bias, no current flows, no attraction, that leaf goes back and the street light goes off. But there's a problem. Now, what is the problem? The problem is when this inverting input voltage increases due to the brightness, a stage will come when both are equal. Look, in the darkness, this output is greater, and this non-inverting is greater, and inverting is smaller. Early in the morning, now this voltage is increasing. It becomes 3, It becomes 4, 5, and 6. When it becomes greater than 5, then definitely there will be negative output and the street light will be switched off. But the problem is when both becomes equal, early in the morning, due to change in the brightness before the sunrise, when both voltage are equal at the input terminal, then output is equal to A naught, difference of the input, no difference, no output. So when there is no output here, this magnetized coil will lose its magnetism. It was a magnet, electromagnet. It was a strong magnet, but when there is a zero output voltage, it will lose its magnetism. During the loss of its magnetism, when both inputs are equal, there is a non-uniform field around it. When electromagnet is demagnetizing itself, the magnetic field around the magnet, around the coil is not uniform, it is non-uniform. And according to Faraday's law, when a coil, when a conductor cuts the non-uniform magnetic field, EMF is induced in it. Look, the coil itself is cutting its own varying magnetic flux. So according to Faraday's law, an EMF is induced in it. And according to Lenz's law, this induced EMF is totally opposite to the source of the magnetic field. So what is the source of the magnetic field? This positive voltage. So definitely the induced voltage will be negative, current will be negative, and this type of the induction is called self-induction. When the coil cuts its own varying magnetic field, EMF is induced, current is induced in it. According to Lenz's law, EMF induced, current induced is opposite to the source, so it becomes negative. Now, for the negative current induced in the coil for the short period of time, this diode becomes conductor because this negative side connected with the negative. When it becomes conductor, current flows back. This terminal output has minimum impedance, ideally 0, but practically 100, very low. So the current flows towards the operational amplifier. When current enters the amplifier due to the low impedance of the output terminal, so it stops working. So this is the problem when both input voltage becomes equal. So there will be self-induction of this coil. Negative current is induced, and due to the current, this op amp is faulty. Now to fix this problem, another diode is connected with this circuit, and that diode is called protecting diode. Look, this is the junction, this connection, and this diode is connected here. And this is DP, protecting diode. Now, after sunset, output is positive, diode is forward biased, current flows through the diode, this coil becomes magnet, it attracts the iron leaf, it makes the contact, and the street light goes on. Now, early in the morning, before sunrise, when both inputs become equal, this output becomes zero. The coil demagnetizes itself due to electromagnetic induction, due to self electromagnetic induction. This current is induced, this EMF is induced. According to Lenz's law, this negative current, when negative current is induced at the junction, it has two possibilities. This diode first, this DP diode. Now, the current has two paths. So both are forward biased, this side negative, this side negative. So there are two possible paths for this negative current. But remember, current always follow the least resistive path. So this is the most resistive path toward the op-amp. So instead of going to this 100 ohm resistance, it goes to the earth through DP. In this way, this operational amplifier is protected and it works for the next night. So this is the working of the operational amplifier in a relay circuit.